Hi, everyone. My name is Matija. I'm a grad student at CCQ, and a part of my research has to do with neural network quantum states. So having attended yesterday, I just want to issue a fair warning that this talk is going to be somewhat different from the ones yesterday, because the goal of this is not to go into kind of the frontiers of research in this field. The goal is to kind of bring everyone along for a little demonstration of what these types of calculation do as a very kind of low variance, high bias introduction into the world of neural network quantum states and the calculations we usually kind of tend to do in this field. All right. So as per usual these days, I guess a Dolly picture that's supposed to impress the audience is present on the title slide, but do with it what you will. All right. Again, what this talk is, just kind of wanted to run you through a bunch of different ideas that kind of orbit the field of quantum physics and neural networks at the same time, and introduce the formalism of variational Monte Carlo that kind of binds them together into kind of a calculation that you can run today that's been fairly well established in the last couple of years. However, what this talk is not is I'm not going to be going out of my way to impress you with various words like superconductivity and superpositions and various other quantum-y sounding buzzwords just for the, I just want to bring everyone along for a ride, and even those who are not super familiar with quantum physics. So do forgive me if I end up erring on the side of caution and kind of go maybe too basic in explaining things rather than just kind of throwing buzzwords at you. But it is what it is. So you're here now. So all right. Just to give you, again, erring on the side of caution, introduction to the notion of why quantum physics is, I guess, in my personal, very biased opinion, kind of more difficult than your classical modeling of just probability distribution, is the example of just classical bits or spins. I think everyone should be at least on some level familiar with the Ising model. If you have a configuration of classical bits, you have things, a single bit has 2 states up and down. If you have a single one, you have up and down. If you have 2 of them, you suddenly have 4 possibilities. For each version of the first guy, you have the two possibilities of the second guy. For 3 bits, you have 8 possibilities. Now, classical physics will tell you that your system can be in any of the 2 to the power of n possibilities that you might find in your system. However, quantum physics is more complicated because superpositions of these states are allowed. Suddenly, the valid state of a system is any linear combination of basis states, quote unquote, which is kind of a buzzword that I'm introducing here, which represents any generic quantum state is a superposition of these guys. And by extension, the definition of the probability distribution over different configurations or outcomes of a measurement is given by the modulus squared of the coefficient in the expansion, also called the wave function. So to kind of bring this on a more abstract level, the formalism is as follows. Given a set of classical configurations or basis states, again, X, just up there on the right, you can expand any generic quantum state in your state space as having this expansion in these basis states, and the probability distribution over the outcomes for anything. It can be classical bits, it can be positions of electrons in an atom, it can be any sort of other type of state space that you can imagine classically. A quantum version of it will include superpositions. And because these coefficients are complex, the kind of point of contact with machine learning or AI, and also the main difference, I would argue, is the fact that on top of a probability distribution, which is just the mod squared of the wave function, you also have a phase function to model with your neural networks. And this is kind of what the entire kind of bread and butter of this whole business of neural network quantum states is, and what makes it difficult is because this phase function exists and things are not entirely positive and normalizable to 1 just by on their own. When you integrate things, there's interference, there are zeros in the things you're trying to say Monte Carlo sample and so on. But all of these things we're going to get to in a second. All right, so not just probability, also a phase makes things complicated, mathematically at least. All right, so kind of to hammer down on some more notation, what we're trying to do, a specific problem that I kind of take an example of and kind of try and chew on it until we get something that connects to AI and machine learning, is the problem of finding ground states of quantum Hamiltonians. Now, all of these are, again, buzzwords that I promised you I wouldn't drill on too much. But essentially what it is mathematically, given this Hilbert space, or the state space that I've introduced earlier, you have an operator H. And associated with this operator, there's an eigendecomposition, or there are eigenvalues and eigenvectors that you're trying to find. And the task of finding the ground state is the same thing as mathematically saying, we want to find an eigenvector of this operator H that lives in an enormously high-dimensional space, We want to find an eigenvector and the associated lowest eigenvalue. So this is the problem we're trying to solve. And in order to do this, at least this program that I'm trying to set up that uses machine learning and neural networks, is doing that by minimizing the Rayleigh quotient. This is the same mathematical quantity written out in 3 different formalisms. You know, mathematicians might write something like this, given a vector psi. Physicists might write something with this bracket notation. That's, you know, some people hate with passion outside of physics. But again, I'm not going to get into the politics of that. And chemists might write something like this on the far right. And the little dog is now wearing a blanket because he's a scientist and he knows all of the 3 things that are listed downstairs. All right. All right, so this is the mathematical problem. If you don't care about physical specifics, it's just the lowest lying eigenvector. If you care about physical specifics, it's the state with the lowest energy out of all of the possible states in the Hilbert space, in the state space that we're describing. So how do neural networks help us? Well, the idea is, as I said earlier, the previous slide, is we're trying to say that because we cannot store all of the exponentially many complex numbers that go into fully describing this state space, what we're trying to do is parameterize it with a neural network. So instead of storing exponentially many x's, we're going to store polynomially many thetas and just query these amplitudes as we go along. So that's basically the idea. All right, so this we've gone through. OK, so the reason why words Monte Carlo even ever go near this discussion of neural networks in quantum physics is because we kind of borrowed a trick from classical machine learning and classical statistics that goes by many different names, but the one I chose to put on the slide is the reparametrization trick, also known as like the reinforce in reinforcement learning. But essentially what it is, because this is just a picture of a variational autoencoder where this trick is used, but not really super important right for this. The trick is you want to be able to calculate expectation values of operators, which is just to say these guys. These quantities, these Rayleigh quotients are also called expectation values in quantum physics. And in order to calculate them, this is how you expand it. And the trick, which is not that sophisticated to begin with, is just to pull out a factor of psi to get a probability distribution on one hand, and whatever's left on the right-hand side is just the thing you call the local operator. In the case of energy, it's the local energy. In the case of, say, momentum, it will be local momentum, and so on. But the trick is, when you have a function that you're sampling from, and we're going to estimate this quantity using the finite sample estimate, because we're going to Monte Carlo sample from psi and then estimate these guys. But again, exponentially large spaces, we cannot do things exactly. Therefore, Monte Carlo sampling helps us. The problem is, if we don't do that, then basically things are impossible to calculate. So we do our best to write things to look as an average, to look like a classical average, even though the thing we're averaging over itself has the neural network in it. So this is kind of what gets slightly interesting mathematically. But regardless, the thing works, the expression is mathematically consistent, and what we can do is ask the next big question in machine learning is, what about the data? What's the kind of, we are doing machine learning here, what about the data set? There is no data. OK, so this is the thing. This is a calculation. As we set up the problem, we only are given an operator. We're trying to find the lowest lying eigenstate of. There are no examples for different systems we're trying to train on. This is where the whole Monte Carlo thing goes in. So basically, the method that does this with no data is called variational Monte Carlo that I'm trying to introduce. And essentially, the trick, even though it's kind of, when you think about it, it's kind of simple, is at each step, I use my favorite Monte Carlo algorithm, a black box thing, to sample from mod psi squared. I obtain a series of classical configurations that I can then use to finite sample estimate both the value of the cost function, or the expectation of the energy, same thing, and the gradients of the thing to go downstairs. So basically, I initialize my quantum state at some point here, and I should be using a tool to point at the screen, I guess. Myself in the process. I'm sorry. All right, so you initialize your quantum state here, both the phase and the probability together, and you would generate Monte Carlo samples for these values of parameters here. And then you would take a gradient step, it would bring you here. Take another gradient step, it would bring you here. And essentially, this energy landscape directly corresponds to the cost landscape in classical machine learning, whereas now it's not something that's defined by data. It's something that's defined by the state itself. On the classical side of things, this is very similar to variational inference, right? It's the similar kind of idea where you would sample from the probability distribution model, And you use the samples from the model itself to estimate gradients from some sort of like KL divergence between your targets and parametrized distribution.
I found this on the web for a series of classical
Shut up. Sorry, Siri decided to look for the words I'm saying. Sorry.
To try to get a picture of what's going on, you're aiming for ground state.
Yeah.
And there are these excited states.
That's right.
Can you use your seat mic for the people on Zoom, please?
Do I think about the excited states as local minima and the ground state as a global minima?
So the landscape here is in parameter space. So that will depend on the parametrization of your wave function. So usually not, because you can, even if that is the case, you can always find a bigger neural network that has kind of a better gradient dependency on the thing. So not generally, sometimes yes.
So I'm trying to think about what, taking your picture seriously with local minima and things you have to tunnel out of. Do you have a physical intuition? What's your physical intuition on that space?
So my physical intuition is as follows. So this kind of windy manifold should be thought of as embedded within Hilbert space. So you have an exponentially large Hilbert space, a subset of which is carved out given a specific variational wave function. That means that every possible state, so you're never going to be classically able to represent all of the possible quantum states in the Hilbert space because there are just too many. And most of them are physically irrelevant to begin with. So what you do is say my neural network defines a subset that I'm interested in, and we just keep our fingers crossed that the ground state is among them. So that means that every possible state representable by my neural network lives on this manifold that's embedded within Hilbert space. And by doing this gradient descent, we're hoping to get closer and closer to the real ground state, which might be slightly outside this variational manifold, as it's called. But we're hoping that this epsilon, let's say that if it's here at the bottom, that this epsilon's not too large. But the specific configuration about hopping in and out of local minima is basically the same argument as with the classical machine learning, where it just magically works if you throw enough parameters at it.
Right. I mean, I guess I'm trying to think about this from the quantum mechanics side of I want to solve for a wave function. I can solve it exactly for single electrons. I start to think about electron-electron interactions as a perturbative correction in the system.
Yeah. So that's
Can
sort
I
of
connect those pictures at all?
Sorry?
Can I connect that to this picture at all?
So what you're describing is like a perturbative expansion. There are certain wave functions. So perturbative expansions are not necessarily variational, which means that they're not the wave functions you get out of doing these expansions are not necessarily lower bounded by some energy from below. So this is kind of a thing you can just prove mathematically. Whereas this, we're directly kind of trying to construct, if you will, an infinite order perturbation theory, or like a wave function that gets at least the relevant terms in the perturbation expansion that will minimize the energy. We're kind of directly optimizing for what we want instead of doing it in term by term, expanding in some coupling constant that's not directly related to what we're trying to do, and which is minimize energy. So it's kind of, doing things differently from a different point of view, I guess. So again, to reiterate what we just discussed slightly, the big picture, and there is, to hammer the pun home, there's a dog looking at the big picture, is, okay, we choose a quantum state. You choose your favorite neural network to represent a quantum state. You take your favorite Monte Carlo sampler, obtain samples from the model, use samples to estimate the energy and its gradients, and go downhill using your favorite optimizer, which is, I guess, Adam at this point in machine learning history. So yeah. All right. So kind of now that we've outlined the algorithm we want to kind of vaguely go through, I want to kind of briefly talk about how these neural network quantum states are different in, I like slight algorithmic details and quirks than to classical machine learning. One of the first things that we've already brought up is that there's no cost function to AD directly. Because you're estimating your cost value from the samples from the model itself, you cannot directly backprop through the Monte Carlo sampler itself. So you're kind of forced to directly, oh, now it's all jumbled up. All right, so I guess I'll try and do it this way. So there's no cost function to AD directly, which means that you're forced to estimate the gradients using the samples. So directly calculating the values of the gradients and then updating using your favorite optimizer, which is kind of not necessarily a roadblock, just a quirk. One of the other things we kind of want to get quantitative accuracy. So there is a direct physical reality connected to lower energies as opposed to higher energies, and like a few decimal places is actually an important difference because there are physical effects that depend, say, exponentially on energy differences, which is kind of a big thing, and we're trying to get things accurately, which is why, as a consequence, for instance, we sometimes run our calculations with float 64s, which GPUs hate, but hey, we want that many digits of precision, and it is what it is, right? As two consequences, for instance, we very often use natural gradient descent as an optimizer, which is kind of second order, but not really, but still kind of, which is, an optimization detail that we can talk about from the side of machine learning later on. But essentially, it's like a second order optimization method that's kind of more expensive to do. And as a consequence, our models have on the order of thousands to tens of thousands parameters, as opposed to millions and billions, which modern day machine learning methods, or like transformers, for instance, have. So for models that we learn, there are very often fundamental constraints along the lines of there's often like a very clear physical system embedded in physical space, which means there's often things like rotational symmetry, translational symmetry, even more complicated things like SU2 spin rotations, and so on. But also more fundamental constraints like fermion and boson exchange symmetries, which means that sometimes we're going to get to that later, but we need neural networks that are explicitly either symmetric or anti-symmetric with respect to permutation of input vectors, which is kind of a challenge that usually you don't have unless you're dealing with like point sets in 3D or something. And finally, there's the sampler. There's the black box of Monte Carlo sampler that you need to plug into the whole thing, which is kind of a choice that will greatly determine the efficiency of your procedure, because if your Monte Carlo sampler is slow, has long autocorrelation times, or just is generally compute heavy, it's not going to be an efficient thing to run, and you kind of need to reconsider what you're doing. And finally, kind of related to the fundamental constraints, we sometimes, these quantum states represented by neural networks have very unconventional inductive biases. So in order to enforce anti-symmetry between certain particles, sometimes determinants are used to kind of, when you change two columns of a determinant, the minus sign pops out, and that's how we very often enforce anti-symmetry of things. To enforce symmetry, sometimes you would do convolutions where not each filter is independent, but filters are connected to connected to each other by physical rotations of filters themselves. So there's actually just one filter, and all of the other filters are just kind of rotations or flips of the one filter that's shared between all of the other guys. This is how you enforce symmetry, for instance. And sometimes, because we kind of want our neural network to output a complex number, because there's if you remember, probability distribution and the phase, sometimes people just do that by having complex parameters within the neural network, which is a whole nother world of pain from the point of view of automatic differentiation, because none of the modern tools really do holomorphic differentiation, and that's kind of a thing that we even want to get into, but it's painful. Yeah. All right. So to give you kind of hammer everything home, a hello world example would be you have, say, a quantum Ising model. Everyone's kind of sort of seen an Ising model at some point in their education, I hope. And this is what a quantum version of it looks like. You have your H that looks something like a combination, like a polynomial in spin operators across a lattice that looks something like this in the top right corner. And at each site lives a variable that's either up or down, at least in the classical case. And you do the whole thing. You sample the thing, you estimate the gradients, you estimate the cost function, and just for eyeballing it, not necessarily remembering it, the expression for the gradient looks something like this. Okay? But the main point is it's an ugly expression that's not very informative to look at. But the point is that these averages here that go around the whole thing are also an average with respect to the Monte Carlo samples of the model itself. So again, if you get a bunch of samples, you can estimate everything you want in the finite sample limit. Yep.
What's E here?
Sorry?
What's E, the quantity
He?
E?
Oh, E, energy. Yes, sorry. So energy is just the average of the Hamiltonian operator defined here.
Okay.
Sorry. All right. Yep.
You were mentioning the issue. This is really like
Reinforcement learning, right? Because you get a gradient that depends on the logarithm of the probability distribution. Is it? Is it something you said? I think you said something like this.
So this is, okay, so often what we parameterize instead of the probability distribution itself is the logarithm of it, or the logarithm of the wave function. If you think about this expression with the square root of p times the phase, what you get is like a real and imaginary part that directly correspond to the log probability and the phase. So what we do in order to maintain accuracy, even for Monte Carlo sampling, you only ever need logarithms of probability distribution. So what we do, we actually say log psi equals some neural network. Right, so, and this is just the derivative of your ansatz. So if you have log psi directly parameterized here, theta are parameters of the neural network, and you can just calculate these gradients using your favorite AD package. All right, so there are like 3 distinct classes of systems in my very biased enumeration of them. So there are, spin systems are the one that we just kind of talked about are usually looked at as toy models. And these guys, there are several interesting neural network architectures that work well for these systems. The ones that were introduced first in 2017, it kind of blasted open the whole field of thinking about neural networks in this context are restricted Boltzmann machines. More recently, in like 2021, I believe, recurrent neural networks have been used for this, which means it's like pixel RNN, if you've ever read this paper from like ancient history in 2016, which is just basically an RNN that goes through the physical dimensions of the system and kind of just outputs autoregressively amplitudes as it goes along, which is an interesting architecture. But in any cases, there are both easy spin systems and difficult spin systems, where the cases of frustrated magnetism, which I'm not going to get into too much, are the ones that are considered difficult. But more importantly and more closer to physical reality, we have the case of bosons, which are particles that have this exchange symmetry. So if there are n particles, and say they have coordinates x, when you exchange 2 of them, your wave function is not allowed to change. Those are usually considered somewhat an easier example, because symmetric wave functions you can show that are connected to what's called a stochastic Hamiltonian, which is a terrible term no one should ever use, which is like a combination of stochastic and quantum, and someone decided that stochastic was a good middle ground here. Considered easier to solve because essentially you can show that the phase is 0 very often for the ground state, which means that the only thing you have to learn is the probability distribution itself. And usually an example for the solution to this problem to enforce specific exchange symmetry is, say, a deep set, which is an explicitly symmetrized neural network, which, again, the paper is linked downstairs at the bottom. And yeah. For fermions, specifically, have the opposite case. When you exchange 2 inputs, you are required to spit out a minus sign, which is a considerably more difficult thing to do. And you can show that the phase itself, the way physicists say the phase is complicated, is to say the problem has a complicated sign structure, which is to say that there's a bunch of zeros in your wave function, and you should think of the wave function as like a very highly dimensional bubble wrap in Hilbert space. There are like nodes of positive values kind of pinned down to 0 by nodal edges. And when you sample, if there are any Monte Carlo people in the audience, they will tell you that Monte Carlo sampling probability distribution that's either gets very small or has zeros is a very problematic thing to do numerically. And this is why this is difficult as well. Yep. All right. And finally, I want to say, this is an example of determinants that's determinant type ansatz that works well for quantum for fermions, invented by Javier, who's sitting here, also like the there, shout out. And yeah, but more closely to physical reality, the reason why we care about fermions really is because electrons are fermions, and electrons live in molecules in real systems. So we want to do quantum chemistry with these types of calculations. And the roadblock we have there is essentially that the interaction is much more complicated than what we've seen before. It's just a bunch of Coulomb terms that look something like this. And there's a bunch of quantum chemical methods that are that exist outside of neural networks with varying degrees of accuracy and varying degrees of computational complexity. But basically, it's a game of picking and choosing your favorite method. But at the end of the day, there's a bunch of industrial and real world applications that depend on getting these properties of molecules related to ground states very, very, very accurately, and it's a very difficult problem. And naturally, someone had the idea of, for instance, let me just show you like one of the state-of-the-art approaches, at least from the neural network side of things, is to throw a transformer at it as a shock to no one. And I just flashing this image here because it's interesting. So it's a transformer. There's a self-attention. There are MLPs, but at the end there's a determinant because again, we're forced to be anti-symmetric in our inputs, and it turns out to work very well, but very well within the context of the field, which means that for very tiny molecules, like these guys over here, you get satisfactory accuracy. So the gray region here is something that's called chemical accuracy. So if you get below the shaded region, you're considered to have solved the problem to a satisfactory accuracy, which is like an industry standard. But if you go outside of it, there's still some accuracy to be picked up by better methods. And I guess even 12 transformer block transformer with the determinant at the end and all of the symmetries built in and all of the bells and whistles on it is still getting the satisfactory accuracy to just a couple of atoms in a molecule. So it's a very difficult problem for any method, including deep learning. And I just want to flash some other uses. So you can use neural networks in this context for various other things than just finding ground states. One of the things is real-time evolution, which is just to say, I want to solve the Schrodinger equation, but I'm giving you an initial state. It's a very high-dimensional PDE solution as opposed to finding an eigenstate of an operator. I'm not going to go through many of these things because I don't have that much time. But essentially why this is interesting is because we want to do quantum control eventually. We want to be able to control tabletop experiments, and in order to do reinforcement learning, quote unquote, in quantum world, we want to be able to have robust real-time simulators in order to poke the quantum state and measure it and do various things to it while we try and control it. And again, this parametrization is useful for that reason as well. The steps are essentially you parameterize your wave function with your favorite neural network, and then you say, now the parameters of my neural network depend on time, on real time. And then you can say, when you plug that, something that looks like this into the Schrodinger equation, you get a nonlinear set of equations in the parameters of the neural network, and you can play the same game, essentially. The algorithm ends up looking very similar, but then some results, there's a paper that we've done about this about a year ago. You can get really long time evolution for systems that are experimentally interesting, and you can get various, quantities related to quantum control that people in labs that have to do with quantum computing are interested in. So that's, I'm not going to get too much into the details. I'm happy to talk about it offline, but in the interest of everyone's time, I'm going to move to the next one. The next one is, for instance, quantum computation. So there you can also ask, okay, if I have a quantum computer on a tabletop right here, and I query it a bunch of times, and it gives me a data set of some sort of quantum data set. How much data do I need to properly learn it using a neural network to reproduce it to some satisfactory level? There are fundamental bounds to this because quantum physics is intrinsically, there are like hard mathematical theorems saying that you cannot completely capture all of the exponentially many amplitudes of an arbitrarily complex quantum state. Now the question is, how far can we push with neural networks? And there's a bunch of work in this direction saying, how much data do you need in order to accurately represent, this is the number of samples, ns, in order to accurately reproduce the quantum state. And this is an instance of the phase function theta being learned correctly over a set of samples, which is the difficult part to do. The probability is usually not that difficult if you got the phase right, and so on. And you can extract various other things. And the other thing you can ask is, okay, but if I have a neural network representing a quantum state, can I do quantum computation on this? If I apply a logic gate to the neural network itself, what does an application of a logic gate look in the parameter space of a neural network? And you can also do this, and this is something we've done a couple of years ago, and we get some really good results for specific cases. So if you design your neural network with good inductive biases, you can do a lot, but for a generic quantum computation, there's no good solution. This is basically the message. Okay, and basically to summarize everything, what I've told you is this. Dogs are cute, point number one. Point number two, VMC, or this algorithm that I've been yammering on about, is very much like the quantum version of variational inference, if you're familiar with this. And you can do a lot of things with it, including finding ground states. You can do time evolution, quantum control, quantum computation, all of these difficult things, provided that you construct your neural networks in a way that includes a bunch of the symmetries and other inductive biases that live in the real world and have to do with quantum physics. Okay, so I've introduced, before I realized there's like a problem session to actually put a slide in, I've kind of put a couple of points to think about to kind of leave everyone vaguely in the back of their heads with. And this is a very biased list of things to consider while, during the break or something. Is there a better way of encoding antisymmetric functions than just putting a determinant at the end of a symmetric thing? Is there a cleverer way of using these like big data language models, transformers, in the quantum world than just making them another big wave function? Because it seems like they're capable of much more than that. And is there a better way to do real time, which is to say, given a very high dimensional PDE, operating, the time-dependent Schrodinger equation specifically, is there a neural network-inspired way that can give me a solution to this that's not the one that I've described before, because that's kind of numerically unstable for reasons that I didn't get into. All right, and finally, a picture of a real dog that's been inspiring all of the fake dogs up to this point. His name is Thor, and he loves you very much.
Okay, so we already had the questions during the talk, but we have time maybe for one short question. Is there a short? Yes. Yeah.
So I have two quick questions about what you're calling variational Monte Carlo. So firstly, what is variational?
Yeah. Variational, that's kind of a historical name. Variational refers to the variational theorem. At the very beginning, let me scroll all the way back up, when I presented the Rayleigh ratio, or whatever, these guys, right? So the statement that all of the eigenvalues, so the minimum of this quantity between all of the psi's, the minimum of this quantity corresponds to the lowest lying eigenvector. That statement is called the variational theorem in quantum mechanics of like 1920s. So when people do variational Monte Carlo, whose goal is to minimize this guy as like a machine learning cost function, then that's using Monte Carlo sampler in the middle. That's ended up being called variational Monte Carlo, even though Monte Carlo is just a component of it.
Yeah, that word is used a lot. Okay.
Yeah.
Okay.
Sorry, it's just overexplaining.
The other quick question I had was, so in the slide where you were talking about generating data, roughly speaking, the Monte Carlo, so usually when you think about sampling, you're thinking about sampling from a probability density, right? But psi is not a probability density.
It is not. We sample from this guy.
Okay, you do. Okay, and then you extract psi from that. Is that?
Yes. So you can rewrite the expression for the cost function and the gradient of the cost function with respect to samples from psi, right? For instance, I give an example of this in one of the slides. Is this, right? So this is the expectation value of the energy. The h is being the Hamiltonian operator. So what you do, you pull out a factor of psi in order to make it look like a classical average over a classical probability distribution, right?
Okay, so your sampling procedure is still dealing with a space of probability density.
A purely positive thing that's normalized and nicely behaving in the classical sense, but just that kind of forces you to rewrite all of the quantum expressions to look like classical averages.
Great,